There was a time in Earth's history when every ocean on the planet became a place where almost no living creature could survive. The most terrifying part was that the culprit was never a living organism. It was the very thing that covers more than 70% of the planet's surface. The very thing that every form of marine life depends on to survive. The very thing that had sustained life for hundreds of millions of years had quietly become a poison. Every breath taken beneath the ocean led to death. No creature, no matter how fast it could swim or how skilled it was at hunting, could escape. Throughout more than 500 million years of Earth's history, no ocean had ever been more dangerous than it was during that period. A time when the planet came dangerously close to losing nearly all life beneath the sea. And once you understand what really happened, you'll never look at the ocean the same way again. To understand the story I'm about to tell, you need to forget everything you think you know about the ocean. Because for most of its history, Earth looked nothing like it does today. Around 250 million years ago, the continents, as we know them today, had not yet formed. All of the planet's land was fused into a single massive landmass, vast, fractured, and blisteringly hot at its center, that scientists call Pangaea. Surrounding Pangaea was something no word can fully describe. Panthalassa, the superocean, a body of water covering more than 70% of Earth's surface and stretching across an area nearly twice the size of today's Pacific Ocean. Seen from space, Earth looked like an almost entirely water-covered world, a giant blue eye with no visible boundaries. But that beauty existed only at the surface. Hidden beneath it was an ocean that was quietly killing life itself. The ancient ocean was unlike the modern ocean in every way that mattered. Its waters were, on average, 8 to 10 degrees Celsius warmer than they are today. That may not sound like much, but for an ocean, that difference marks the boundary between a habitable ecosystem and a gigantic cauldron slowly coming to a boil. The concentration of dissolved oxygen in the water was far lower than it is today. Ocean currents behaved differently and did not carry oxygen down into the deep waters through the kind of global circulation that sustains the modern ocean. What did that mean? It meant that below the surface, at a certain depth, there was a boundary, a hidden, invisible boundary. Beneath it lay a world without oxygen, a world of darkness and decay. A world inhabited by organisms that needed neither sunlight nor air to survive. And those very organisms would come close to wiping out nearly all life on Earth. But before we get there, let's meet the predators that ruled the upper waters, the monsters with bodies, teeth, and eyes. The kind of creatures that, at least, you could see before you died. We begin in the Jurassic period, around 180 million years ago. Pangaea had begun to break apart. The continental fragments drifted away from one another in different directions. In the widening gap between them, a new sea gradually emerged. It was the Tethys Sea, a sunlit ocean that would become one of the greatest centers of life on Earth. From the surface, Tethys looked like paradise, warm, crystal clear, and teeming with coral reefs and fish. But don't look at the surface. Look deeper. There, in the dark blue water, ruled the apex predator. It was Leopleurodon, a species of pliosaur, unlike any marine predator the modern world has ever known. Its body measured about 6 to 7 meters in length, smaller than Hollywood once portrayed. But don't let that fool you. Its head alone made up nearly 1/4 of its total body length. Inside, that enormous skull was a set of jaws with an estimated bite force many times greater than that of a great white shark, built not for chewing, but for tearing flesh apart. At the same time, in other layers of the Tethys Sea, lived the ichthyosaurs, creatures that resembled dolphins, but were faster, far more aggressive, and, in some species, gigantic enough to reach 21 meters in length, larger than today's humpback whales. They moved in groups, coordinating like an army, driving their prey into the ocean's blind spots, before attacking simultaneously from multiple directions. But in the end, the Tethys Sea disappeared. It was crushed by the collision of tectonic plates as Asia and Europe slowly converged over millions of years. Today, its only surviving remnant is the Mediterranean Sea, small, peaceful, and filled with sailboats and tourists. Few people realize that beneath the blue waters of Santorini or the Amalfi Coast once lay the domain of creatures like these. Then, around 80 million years ago, during the late Cretaceous period, the world changed again. On land, the dinosaurs were at the height of their power. Tyrannosaurus rex roamed the regions that would one day become Montana and Alberta. Triceratops grazed across plains that no longer exist. But beneath the sea lurked a predator that even Tyrannosaurus rex would never have wanted to encounter. At that time, North America was not a single continuous landmass. Instead, a vast inland sea, the Western Interior Seaway, split the continent in two, stretching from what is now Canada all the way to the Gulf of Mexico. Imagine a river so wide that you cannot see the opposite shore, so vast that it had waves, storms, and true ocean currents. The undisputed ruler of those waters was Mosasaurus. It was neither a shark nor a marine crocodile. It was an evolved marine reptile, a distant relative of today's lizards and snakes that had, in effect, claimed the ocean as its own and evolved specifically to dominate it. Its length reached 17 to 18 meters, with an estimated weight of more than 15 tons. But don't focus on the numbers. Picture this instead. A double-decker bus is about 12 meters long. A Mosasaurus was longer than that bus by another half a bus. and every inch of that length was muscle, scales, and 2 rows of teeth. The outer row was for biting. The inner row, a second set of teeth growing along the roof of its mouth, acted like a conveyor belt, pulling prey deeper into its throat. Once a victim entered its jaws, there was no escape. But Mosasaurus was not alone. In those same waters lived Elasmosaurus, a species of plesiosaur with a neck measuring 8 meters long, longer than the rest of its body, gliding beneath the surface like a gigantic cobra, searching for the perfect angle to strike. There was also Xiphactinus, a bony fish reaching 6 meters in length, so fast that it could swallow another fish nearly its own size in a single snap. Fossils of Xiphactinus are often discovered with another fish still intact inside the stomach, suggesting that its final gulp was, in some cases, also its last meal. The western interior seaway was a bottomless killing ground. Every layer of water was a battlefield. Every additional meter of depth meant another predator waiting in ambush. And if you fell into those waters, you wouldn't have time to scream before the sound could ever reach the shore. From about 23 million to 3 million years ago, during the Miocene and Pliocene epochs, another ruler emerged. This is the one you've probably heard of, the one movies have tried to recreate, but have never truly gotten right: Megalodon. Megalodon is not the subject of conspiracy theories, claiming it might still be alive in the deep ocean. Megalodon is extinct, but throughout the roughly 20 million years it existed on this planet, it stood alone at the very top of the food chain in every ocean on Earth. There were no exceptions. Its length ranged from 15 to 20 meters. It is estimated to have weighed between 50 and 70 tons, heavier than 10 average-sized trucks stacked together. The largest tooth ever discovered measures 18 centimeters, nearly the distance from an adult's wrist to the tip of the fingers. Scientists estimate its bite force at between 108,000 and 182,000 newtons. By comparison, a great white shark generates a bite force of about 18,000 newtons. Megalodon bit with roughly 10 times the force. But the numbers alone don't tell the whole story. Megalodon did not hunt fish. It hunted whales. Not because there was nothing else to eat, but because an animal of its size required a food source that could match its enormous energy demands. And during the Miocene epoch, whales had already become the largest animals in the ocean. Whale fossils from that period bear wounds that tell their own story. Deep bite marks on the fins and tail reveal attacks that were anything but random. They point to a calculated strategy: disable the whale's ability to swim first, then finish the kill. The evidence is unmistakable. It hunted like an assassin, and an assassin never rushes. An assassin knows its prey has nowhere to go. For roughly 20 million years, every time a whale surfaced for air, every time a calf drifted too far from its mother, every time an aging whale slowed down ever so slightly, that was the moment Megalodon had been waiting for. The oceans of the Miocene belonged to Megalodon. Everything else was simply potential prey. A pliosaur could tear you in half with a single bite. A mosasaurus could swallow you before you even realized what was happening. A megalodon could crush you along with the vehicle you were sitting in. All of them were terrifying. And yet, in a way, they still left you with one final shred of dignity. You knew what was killing you. You could see it. You could fear it. And that fear, however futile, was still a fundamentally human response. But the most dangerous ocean in Earth's history offered you no such mercy. It had no teeth for you to see, no eyes to meet, no shape you could swim away from. It was the water itself. Around 252 million years ago, the ocean decided to bring almost everything to an end. This event is known as the Permian-Triassic mass extinction. Scientists refer to it by a name that needs no further explanation: the Great Dying. It was the largest, deadliest, and most comprehensive extinction event in Earth's 4.5 billion year history. The extinction event that wiped out the dinosaurs 66 million years ago, the one we have turned into movies, books, and museum exhibits, eliminated about 75% of all species. By human standards, it was an unimaginable catastrophe. But the Permian-Triassic mass extinction wiped out approximately 96% of all marine species and about 70% of terrestrial species. Out of every 100 species swimming, crawling, slithering, or living in the oceans, 96 vanished forever, leaving behind nothing but fossils and questions that scientists are still trying to answer centuries later. Earth came dangerously close to becoming a dead planet. It began in Siberia. Around 252 million years ago, a colossal volcanic system known to geologists as the Siberian Traps erupted. This was no ordinary volcanic eruption. It was something for which everyday language has no adequate description. Lava poured out continuously, covering an area roughly the size of present-day Europe, and the eruptions may have continued without interruption for millions of years. Enormous quantities of carbon dioxide and methane were pumped into the atmosphere. Earth's temperature soared, and as the planet warmed, so did the oceans. This is where the mechanism became truly terrifying. As water grows warmer, its ability to hold dissolved oxygen decreases. Less oxygen allowed anaerobic bacteria, organisms that had existed for billions of years, dating back to a time before Earth had oxygen, when the atmosphere was a toxic mixture of gases, to multiply explosively in the oxygen-starved depths of the ocean. Those bacteria released hydrogen sulfide, or H2S, Hydrogen sulfide is the gas known for its distinctive rotten egg smell. You may remember it from chemistry class. It sounds harmless enough. But at high concentrations, around several hundred parts per million in the air, it first paralyzes the olfactory nerves, leaving you unable to smell it at all. Then, it attacks the respiratory system, the central nervous system, and finally, the heart. From the moment of exposure to the loss of consciousness can take only a matter of seconds. By the end of the Permian period, H2S was no longer confined to isolated pockets of pollution. It had permeated the entire deep ocean, spreading slowly and relentlessly through the water like a poison moving through a living body. But H2S did not remain underwater. Once its concentration became high enough, it began escaping from the ocean's surface and spreading into the atmosphere across the globe. Scientists have uncovered geological evidence indicating that enough H2S entered the atmosphere to damage the ozone layer, the protective shield that blocks much of the sun's ultraviolet radiation. As the ozone layer weakened, ultraviolet radiation intensified. Plants on land, already struggling under soaring temperatures, were now being scorched from above by intense UV radiation. The ocean was not merely dying, it was killing the land. Within a span that geologists estimate lasted only 60,000 years, a mere blink of an eye on the geological timescale, approximately 96% of all marine species disappeared. The ocean had become a place where life was no longer possible, and that deadly condition spread everywhere, slowly, relentlessly, and beyond anyone's ability to stop it. After that event, Earth required at least 10 million years before its oceans even began to recover. 10 million years, a span roughly 2,000 times longer than the entire history of human civilization since the dawn of agriculture, during which most of the world's seas remained almost completely empty. Scientists refer to this interval as the coal gap, a gap in the geological record where marine fossils are almost entirely absent, not because they failed to fossilize, but because there was almost nothing left to fossilize. It was the most dangerous ocean in Earth's history, not because something living in it wanted to kill you, but because the ocean itself had died, and in its death, it dragged nearly everything else with it. The conditions that gave rise to the Great Dying, warming oceans, oxygen depletion, explosive growth of anaerobic bacteria, and the buildup of hydrogen sulfide are not merely a closed chapter in Earth's history. They are beginning to appear again. Dead zones are what oceanographers call regions of the ocean, where oxygen concentrations have fallen to nearly zero. Almost nothing can survive there. Fish flee. There are no crabs, no shrimp, nothing but algae and bacteria. The Gulf of Mexico now contains a dead zone, covering an area nearly the size of the state of New Jersey. The deep waters of the Baltic Sea become completely depleted of oxygen during the summer. The coasts of West Africa, Oregon, and the Arabian Sea have all joined a list that continues to grow with each passing decade. This time, the cause is not the Siberian traps. Instead, it is the combined effect of climate change, which warms the oceans and reduces dissolved oxygen, together with nitrogen pollution from agricultural fertilizers washing into the sea. That excess nitrogen fuels massive algal blooms, and when those blooms die and decompose, they consume the remaining oxygen. The mechanism may be different, but the outcome is strikingly similar. Oxygen disappears, and anaerobic bacteria take over. And those hydrogen sulfide producing anaerobic bacteria, the same organisms that helped drive the Great Dying 252 million years ago, are still here. They lie dormant on the floors of oxygen-starved seas. They need no sunlight. They need no oxygen. They need nothing except the right conditions to flourish again. They have had 3 billion years to be patient. The strange thing is that some organisms survived the Permian-Triassic mass extinction. Their descendants are still swimming, crawling, and thriving in today's oceans. Sharks first appeared before the Permian period, around 450 million years ago, and survived all 5 of Earth's mass extinctions. That was no accident. Sharks are living proof that some evolutionary designs are so remarkably successful that they have required almost no fundamental change for hundreds of millions of years. Nautilus, with its beautifully spiraled shell that looks like a work of art, is almost identical to its ancestor from 500 million years ago. It has barely changed because it was already perfectly adapted to survive everything Earth could throw at it. And those anaerobic bacteria, the organisms that existed long before Earth had oxygen, that survived the Great Dying, and that now lie waiting at the bottom of today's dead zones, are a reminder that the oldest and most primitive forms of life on this planet never truly disappear. They simply wait. The next time you stand on a beach, gazing toward the horizon, where the sea meets the sky, remember that beneath that surface lies 4 billion years of history. A history of rulers that rose and vanished. A history of things with no names and no recognizable forms that nearly brought the entire story of life on this planet to an end. The ocean is not our backyard. We are merely its temporary visitors. The ocean at the end of the Permian period, where not teeth, not size, but the water itself became poison, is my answer to today's question. Now I'd like to hear yours. After everything you've just seen, where do you think the oceans of the 22nd century will rank on this list? Leave your thoughts in the comments below. I read every one of them, and I'll feature some of the best comments in the next video. If this video changed the way you see the ocean, subscribe and turn on notifications so you don't miss the next episode next week. the only organism on Earth that survived all 5 mass extinctions. It's not a shark. It's not a cockroach. The answer is much smaller than you think, and that's exactly what makes it so much more unsettling. See you next time.